Welcome. Today we're diving into the fascinating world of chemistry to explore a concept that often works behind the scenes: promoters. While catalysts usually get all the attention for speeding up chemical reactions, promoters play a crucial supporting role. They don't directly participate in the reaction, but their presence can make catalysts much more effective. In this video, we'll break down what promoters are, how they function, and why they matter in both industrial and laboratory chemistry. Let's start by understanding the basics and setting the stage for a deeper exploration of this essential concept. Promoter in chemistry is a substance added to a catalyst to enhance its performance. Unlike catalysts, promoters are not directly involved in the chemical transformation itself. Instead, they work by improving the efficiency, selectivity, or stability of the catalyst. Think of a promoter as a behind-the-scenes helper, making sure the catalyst can do its job better. This distinction is important because it highlights the subtle yet powerful influence promoters have on chemical processes. Understanding this definition sets the foundation for exploring their real-world applications. It's easy to confuse catalysts and promoters, but their roles are distinct. Catalysts actively participate in the reaction mechanism, lowering the activation energy and increasing the reaction rate. Promoters, on the other hand, do not take part in the reaction itself. Instead, they modify the catalyst's properties, making it more effective. This difference is crucial in industrial chemistry, where optimizing reaction conditions can lead to better yields and lower costs. By understanding how promoters complement catalysts, chemists can design more efficient processes. Promoters work in subtle but significant ways. They may change the physical or chemical environment of the catalyst, making it more active or selective. For example, a promoter might alter the surface structure of a solid catalyst, allowing reactants to interact more efficiently. In other cases, promoters can stabilize the catalyst, preventing it from degrading over time. These effects are often specific to the catalyst-promoter combination, which is why research in this area is so important for advancing chemical technology. Motors come in many forms, depending on the reaction and catalyst involved. Some are metals, such as potassium or aluminum, while others are nonmetals or even organic compounds. The choice of promoter depends on the desired effect, whether it's to increase activity, improve selectivity, or enhance stability. Each type of promoter interacts differently with the catalyst, and selecting the right one is a key part of catalyst design. Let's look at some common examples in the next scene. Metal promoters are widely used in industrial catalysis. For instance, potassium is often added to iron catalysts in the Haber-Bosch process for ammonia synthesis. The presence of potassium increases the efficiency of the iron catalyst, leading to higher yields of ammonia. Other metals like aluminum or copper can also serve as promoters, each bringing unique benefits to the catalytic process. The selection of a metal promoter is based on the specific needs of the reaction and the properties of the catalyst. Not all promoters are metals. Nonmetal promoters, such as certain oxides or organic molecules, can also play a significant role. For example, silica or alumina is often used to support and promote catalysts in petrochemical processes. These nonmetals can modify the surface area or acidity of the catalyst, leading to improved performance. The versatility of nonmetal promoters allows chemists to tailor catalysts for a wide range of reactions, making them invaluable in both research and industry. Organic compounds can also act as promoters, especially in fine chemical synthesis. These molecules may interact with the catalyst or the reactants, influencing the reaction pathway. For example, certain amines are used as promoters in hydrogenation reactions, helping to increase selectivity for the desired product. The use of organic promoters is an area of active research, as chemists seek to develop greener and more efficient catalytic systems. Motors are essential in many industrial processes. Their ability to enhance catalyst performance can lead to significant economic benefits, such as higher yields, lower energy consumption, and reduced waste. In the petrochemical industry, for example, promoters are used to improve the efficiency of cracking catalysts, which are vital for producing fuels and chemicals. By optimizing promoter use, industries can achieve more sustainable and cost-effective operation. In the laboratory, promoters are invaluable tools for chemists. They allow researchers to fine-tune reactions, explore new catalytic systems, and develop innovative materials. By experimenting with different promoters, scientists can discover new ways to control reaction rates and selectivities. This flexibility is crucial for advancing our understanding of chemical processes and for developing new technologies that benefit society. The concept of promoters has evolved over time. Early chemists noticed that certain additives could improve the performance of catalysts, even though the underlying mechanisms were not well understood. As analytical techniques advanced, scientists began to unravel the complex interactions between promoters and catalysts. Today, the study of promoters is a vibrant field, with ongoing research aimed at discovering new materials and application. Promoters can influence catalysts in several ways. They might change the electronic properties of the catalyst, alter its surface structure, or affect the way reactants interact with the catalyst. These mechanisms are often complex and can depend on the specific combination of catalyst and promoter. By studying these interactions, chemists can design more effective catalytic systems for a wide range of application. One common way promoters work is by modifying the surface of a catalyst. This can increase the number of active sites available for the reaction or change the way reactants are adsorbed. For example, adding a promoter might create new sites that are more selective for a particular product, leading to higher yields and fewer byproducts. Surface modification is a key strategy in catalyst design. Motors can also change the electronic environment of a catalyst. By donating or withdrawing electrons, they can make the catalyst more reactive or selective. These electronic effects are especially important in reactions involving transition metals, where small changes can have a big impact on performance. Understanding these effects helps chemists design catalysts that are both efficient and selective. Another important role of promoters is to stabilize catalysts. Over time, catalysts can degrade or lose their activity due to harsh reaction conditions. Promoters can help prevent this by protecting the catalyst from deactivation. For example, certain promoters form a protective layer on the catalyst surface, shielding it from poisons or extreme temperatures. This stabilization extends the catalyst's lifetime and reduces the need for frequent replacement. Selectivity is a key goal in many chemical reactions, and promoters can play a major role in achieving it. By modifying the catalyst's properties, promoters can direct the reaction toward the desired product, minimizing unwanted side reactions. This is especially important in the production of fine chemicals and pharmaceuticals, where purity and yield are critical. Selectivity enhancement is one of the most valuable contributions of promoters in modern chemistry. Classic example of promoter use is the Haber-Bosch process for ammonia synthesis. In this process, iron serves as the main catalyst, while potassium acts as a promoter. The potassium increases the activity of the iron catalyst, allowing the reaction to proceed more efficiently at lower temperatures and pressures. This innovation has had a huge impact on global agriculture by making fertilizer production more efficient and affordable. In the petrochemical industry, promoters are used to enhance the performance of catalysts in processes like catalytic cracking. For example, rare earth metals are added as promoters to zeolite catalysts, increasing their stability and activity. This leads to higher yields of valuable products like gasoline and olefins. The use of promoters in petrochemicals demonstrates their importance in large-scale chemical manufacturing. In laboratory settings, promoters are often used to improve the selectivity of hydrogenation reactions. For instance, adding a small amount of sulfur as a promoter can help produce specific products by inhibiting unwanted side reactions. This level of control is essential for synthesizing complex molecules in research and pharmaceutical development. Promoters can also contribute to greener chemistry. By making catalysts more efficient, they help reduce energy consumption and minimize waste. This is particularly important in large-scale industrial processes, where even small improvements can lead to significant environmental benefits. The development of new promoters is a key part of the effort to make chemical manufacturing more sustainable. Despite their benefits, studying promoters can be challenging. Their effects are often subtle and can depend on many factors, such as the type of catalyst, reaction conditions, and the presence of other additives. Advanced analytical techniques are needed to understand how promoters work at the molecular level. Overcoming these challenges is essential for developing the next generation of catalytic systems. To study promoters, chemists use a variety of analytical tools. Techniques like spectroscopy, microscopy, and surface analysis allow researchers to observe changes in catalyst structure and composition. These methods provide valuable insights into how promoters interact with catalysts and help guide the design of more effective systems. Green chemistry focuses on designing processes that minimize environmental impact. Promoters play a key role by enabling more efficient reactions, reducing the need for harsh conditions or toxic reagents. By improving catalyst performance, promoters help make chemical processes safer and more sustainable, contributing to a cleaner and healthier environment. The future of promoter research is bright. Scientists are exploring new materials and combinations to create even more effective promoters. Advances in nanotechnology and computational chemistry are opening up new possibilities for designing catalysts and promoters at the atomic level. These innovations promise to revolutionize chemical manufacturing and lead to more sustainable technologies. While promoters are most commonly discussed in industrial and research settings, their impact reaches into everyday life. From the fertilizers that help grow our food to the fuels that power our vehicles, promoters play a hidden but vital role. Understanding their function helps us appreciate the science behind the products we use every day. Innovation in promoter research is driving progress in many fields. By developing new promoters, scientists can create catalysts that are more selective, efficient, and durable. These advances lead to better products, lower costs, and reduced environmental impact. The ongoing search for better promoters is a testament to the power of chemistry to solve real-world problems. Let's recap what we've learned. Promoters are substances that enhance the performance of catalysts without directly participating in the reaction. They can be metals, nonmetals, or organic compounds, and their effects include increasing activity, selectivity, and stability. Promoters are essential in both industrial and laboratory chemistry, contributing to more efficient and sustainable processes. Promoters may not be as well known as catalysts, but their impact is undeniable. By making catalysts more effective, they help drive progress in science, industry, and sustainability. As research continues, we can expect even greater contributions from promoters in the years to come. Their story is a reminder that sometimes, the most important players are those working quietly in the background. As we look to the future, the study of promoters will remain a dynamic and exciting field. With new technologies and a deeper understanding of chemical interactions, chemists are poised to unlock even more potential from these remarkable substances. Whether in industry, research, or everyday life, promoters will continue to play a vital role in shaping the world around us. Thank you for joining us on this journey through the concept of promoters in chemistry. We've explored their definition, mechanisms, types, and real-world applications. Promoters may work quietly behind the scenes, but their influence is profound. As you continue your study of chemistry, remember the important role these substances play in making chemical reactions more efficient, sustainable, and innovative.